All right, we'll look at two things. The first thing we're going to look at is something called electron channeling contrast imaging. In abbreviation, it's called ECCI, like ECCI. The second technique, or second relevant technique we're going to discuss is electron backscatter diffraction. In abbreviation, we have EBSD. So this is called EBSD. Let's do a very quick recap of what we learned a couple of weeks ago. We focused on electron beam material interaction. We discussed there are three types of information we can generate. The first is secondary electrons. The second is backscattered electrons. The third is X-ray. Then in this case, in today's class, as well as next week's class, we'll focus on the backscattered electrons. Let's look at the first part of ECCI. So part one. This is ECCI. We'll start by looking at a very simple example. For those who are doing research in metals and ceramics, for most metals and most ceramic systems, they are made of crystalline, like grains in the material. So if you have something dense and you do mechanical polishing, you get a flat surface. In most of the cases, the flat surface is like mirror-like surface. Assume you have a grain boundary here. So this is the grain boundary. Now I'm going to use green color to show some lattice planes. For the grain on the left, the lattice planes look like this. It's inclined to the surface. Okay. For the grain on the right, we have lattice planes like this. So let's just label that. So this is the grain boundary. Grain boundary. And the green lines, those are lattice planes. I didn't draw the lattice planes very well because they should be equal spaced. Like I do have some variation here, but in the material, the lattice planes spacing is a fixed number. On top, above the surface, we have the electron beam coming into the material. So focus on the grain on the left. The electron beam will travel into the material, then bounce back as the backscattered electron. So this is the electron. Looking at, like, as the beam scans across the specimen surface, the beam now has moved to the grain on the right. Let me ask you, can the electron travel deeper into the material, or more or shallower in the material before the electrons getting spit out? Take a guess. Like, can the electron travel deeper or shallower in the grain on the right with the same beam energy?
I think deeper, because Between lattice plane, there is less force.
Sorry, did you say deeper or shallower?
Yes.
Deeper. Great. Yeah, you're right. You're exactly right. The electron will grow, will travel deeper in the material before the electron can scatter. The reason is because now you have these lattice planes aligned in the same direction of the electron beam. The empty space between the lattice planes, they act like channels. So that's where the word channeling comes from. The electron on the right can channel deeper. So this is the electron. So the one on the right can channel deeper into the material. Since the electron channels deeper, it's more difficult for the electron to get out. It's kind of like you're doing some cave exploration. The deeper you go into the cave, the less likely, I wouldn't say the less likely, the more difficult you can come out. It's the same idea. For the electron, the incoming electron or the incident electron, if the electron can channel deeper into the material, then it scatters. It's less likely for that to come out. So at the granular level, if we look at the contrast, the contrast, for the grain on the left, the electron travels not as deep, so it's short distance into the material. Then it has higher probability to escape the material. If there's a higher probability to escape, then we get more information, we get more counts or high intensity, more BSD counts. If there are more counts, then it will appear to be brighter. For the grain on the right, it channels deeper into the material, so it has lower probability to escape. If the electrons have lower probabilities to escape, then we have less BSE counts. And this grain will appear to be darker. The grain on the left appears brighter. The grain on the right appears darker. This gives you what we call channeling contrast. There are a few notes I want to make here. The first is by using the channeling contrast is much, much weaker than Z contrast. You can only use channeling contrast to highlight the grain orientations if your chemistry is homogeneous. If you have two phases, one has higher Z, the other has lower Z, like one phase is rich, for example, say in copper, another phase is rich in aluminum, then the Z contrast will overwhelm the channeling contrast. If you have like a very well-designed alloy, or like in some ceramics, it's a single-phase material. You polish your sample really well. Then you put the sample in SEM, turn on the BSE detector. You will see different grain orientations if you have done a really good polishing job. The second note is what we see here. We can use this information, but the information is qualitative rather than quantitative. So qualitative orientation information. By using ECCI, you can measure grain size. It's not a problem at all. But you cannot tell this grain is at 111, that grain is at 115, another grain is at like 120, 100. You can only tell they are of different orientations, but you cannot tell exactly what orientations they are. For the students who do research in polymer, this technique is like ECCI as well as EBSD. You cannot really do too much. The ECCI and EBSD, they are very useful for people who work on dense samples, like you sinter some ceramic materials to look at the orientation. You have a piece of metal, you like to know the grain size. This will be a very effective way to do that. Any questions about the channeling contrast to highlight orientation information before we move on? Okay, so actually I forgot to write down. So this is to use ECCI to reveal orientation information. So we put a star. So ECCI to reveal orientation information. In addition to revealing the orientation information, we can also use ECCI to reveal dislocations. So put another star. So ECCI to reveal dislocations. The idea is very similar to the orientation. So let's just draw a very simple model of dislocations. Sorry, too close. Let me draw that down here. Okay, and on the left, we have the perfect crystal structure, but on the right, we have a dislocation. Let me see. Okay, we have constructed the lattice. We have an edge dislocation here because we have half plane missing. Up here we have 1, 2, 3, 4, 5, 6 atomic planes. So 1, 2, 3, 4, 5, 6. But down here we only have 5. So 1, 2, 3, 4, 5. There's extra half plane missing, leading to the edge dislocation. Let's look at the electron beam. When we scan that from the left to the right, what's going to happen? So when we have this specific arrangement, we have electron coming there, like this. The lattice on the left is perfect. So we have good channeling. If we have good channeling, so in the matrix, we have good channeling. If we have good channeling, we have less backscattered electrons coming out. So less BSE count. If we have less signals, then the grain will appear to be dark. So this is when the electron beam is hitting the perfect lattice without dislocation. But when the beam scans to the right, there's a local bending here. The electron cannot easily channel through this bent lattice plane. So instead of going further, more electrons will just come out like this. So when we have a dislocation, especially when the dislocation is around the dislocation core structure, where the lattice bending is most severe, then we have poor channeling. When we have poor channeling, we have more BSE bouncing back. And the dislocation line or the regions around the dislocation will appear to be bright. In this case, in this specific setting, your grain will appear dark in SEM, but dislocations will appear to be bright lines in the material. Any questions? This is a very cost-effective way to image dislocations, comparing using TEM. But of course, using TEM, you can get a lot more information about the dislocations. But in your case, if you just want to look at the dislocation distribution without worrying too much about Berg's vector, slip plane, this kind of information, ECCI can be a very cost-effective way to reveal the information. Okay, there's one note though, before we move on. So there's a note. In this specific setting, we said the matrix is dark, the dislocation line is bright, but if we slightly change the crystal orientation, assume we have the electron beam kind of like coming in this way. In the magenta electron beam case, in this case, the dislocation actually offers better channeling. So the dislocation will appear to be dark and the matrix will appear to be bright. So the exact contrast you see in dislocation imaging using ECCI depends on the exact crystal orientation of the material. So the contrast can change. Depending on the exact crystal orientation. What this tells you is also, it is highly possible you have dislocations in the grain, but both the matrix, like the crystal itself, as well as the regions around dislocation core structure, it doesn't give you a good channeling contrast. It is possible as well. So what people usually do is they prepare the SEM sample, then get the surface really, really nice. Then they put it in SEM, turn on the BSE mode, then just look around. Wherever they see dislocations, they take images. If you don't see dislocations, it does not mean the dislocations are not there. It tells you the imaging condition is not ideal for dislocation imaging. Any questions before we move to EBSD? Any questions about channeling contrast? using ECCI. One more thing I guess I've got to mention is the sample quality has to be really good. The sample has to be, the sample surface has to be really well polished and without any artifacts that may be introduced from sample prep. When you have a clean sample surface, that's when ECCI gives you the best information. The reason is because ECCI contrast is pretty low. If you have some dirt, if you have some oxide layer on the surface, it can wash out the contrast. All right, let's move to the second part, EBSD. EBSD is not easy to understand the first round. It may take you some time to digest. So part 2. For those who haven't seen EBSD maps, those maps are the colorful SEM-based maps you usually see in the papers. The colors really are at the granular level. Each grain will have a different color. Then the color is associated with the exact orientation of the grain. Okay, let's look at how EBSD works. Before doing that, we'll introduce a type of diffraction called Kikuchi diffraction, or Kikuchi pattern. What happens in Kikuchi pattern is we have the material. The scattering or the diffraction is not one step. Instead, it's a two-step process. So let's just draw that first, then I'll write that down for you. So we have the electron beam coming into the material. Okay. What happens is the material will first undergo inelastic scattering. So it will just scatter in all random directions. After that, then the electrons will undergo Bragg diffraction or Bragg scattering. Then this one be then what happens here is after scattering twice, it will form a band. And this band is called Kikuchi pattern. So let me write that down and explain more on this. So the first step, so Kikuchi scattering or Kikuchi pattern formation is a two-step process. The first step is called inelastic scattering. Or to be more precise, it should be called incoherent scattering. There are a few properties associated with inelastic scattering. The first is there's loss in energy. The second is it follows, like the result is a random walk. If we collect diffraction at this stage, so it doesn't give us any diffraction pattern. Instead, it will be just background noise. The example I can think of is if you go clubbing, basically you enter the dancing floor, then you just walk around randomly. So this is inelastic scattering. It's incoherent. Let me rephrase. It's kind of like a group of you and your friends. You walk in the same direction to a nightclub. Then upon entering then you guys just disperse and just dance on the dancing floor. So like at the beginning, you guys were walking in the same direction, but after entering the dancing floor, you go random. You go random. This is the first step. The second step is Bragg diffraction. It's elastic scattering. So the second step is elastic scattering. That's the concept you're more familiar with when people talk about diffraction. When you shine a laser light through like a grid, then you will form diffraction patterns. That's exactly the same thing here. Then for elastic scattering, like after the random walk, what happens is there's no loss in energy. So no loss in energy. That's why it's called elastic. Then it's not a random walk. More technically, what happens is this is Bragg diffraction of inelastically scattered electrons. Then each set of planes in the material will give rise to one set of Kikuchi line. Let me just continue with the like the nightclub dancing kind of analogy. So assume like you and your friends, you enter the club like in the same direction. So all of you are traveling the same direction. But after like entering the club, you undergo random walk. But there's something going on in the club. If there's someone famous going to pull up a show, then all of you will follow the same direction to maybe go to watch the performer or to watch like the actor or actress. Then all of you will go in the same direction again. That forms the Kikuchi pattern. So to kind of like wrap up what we're talking about here, for Kikuchi pattern formation, you have to undergo two-step scattering. You have to first undergo the inelastic scattering to form a random walk. It's kind of like creating a point source. Then after that, you undergo the well-defined, well-predictable elastic scattering by various planes in the material. If there's only inelastic scattering happening, then you will only form the background noise. There's no pattern here. It doesn't tell us about the lattice information, the crystal plane information. If you only have the elastic scattering without, like, without the first step of random walk, you will not get Kikuchi bands. Instead, you'll get diffraction spots. If you do not understand this, it is okay, because when we show the PowerPoint slides, you will see some examples. You'll see some examples. The main takeaway message here is to make sure you know that for Kikuchi patterns to form, you have to undergo the inelastic scattering first, then elastic scattering to see those. Let me ask you, if I reverse the process, if the electrons, they undergo the elastic scattering, then they undergo the inelastic scattering, what's going to happen? In the nightclub, it's kind of like all of you walk into a nightclub in the same direction. As soon as you enter the nightclub, there's a show going on, then everyone's so well aligned to watch the show. After that, the show's over, then you guys will undergo like a random walk. What information do I collect from the diffraction? Do I get spots? Do I still get Kikuchi pattern? Or do I only get background noise? Any guesses? If we undergo the elastic scattering first, then inelastic scattering, what information or what kind of information we're getting?
Do you get any information?
Can you say that again?
I don't think, or I wouldn't think that you really get any information. Or
Excellent.
you like, yeah. Yeah.
Go on.
I just don't think that you get any information from it.
Very good, very good. So this will be just background noise. Just think about, like, in the club, there's a show going on. So you guys well-aligned walk, like you guys walked in a straight line, follow the lane or whatever. Then you watch the show. After the show, when the show's over, you guys go crazy and buying drinks, doing dancing. It's random walk. If it's random walk, there's no information. It's just the background noise. Then for the pure elastic scattering case, it's more like you're watching a show, maybe like in the opera house. You walk together in the same direction into the entrance. As soon as you enter, there are seats, like, reserved. Then all of you will walk in the same direction, take your seats. So that's when you get the well-defined diffraction spots. Okay. So let's look at the what we're gonna see in the Kikuchi diffraction. So let's just use the cubic structure as a model. Okay, if we look at the 100 set of planes, and we have the detector here. It's bad, should be circular. Okay. Let me ask you how many 100 planes you see if I shine electron beam in this way. Let me rephrase a little bit, like how many 100 planes are parallel to the electron beam direction? Any guesses?
Two.
Two, excellent. So we have front and back, as well as the side, like left and right. So in the detector, the diffraction pattern will look something like this. Because they are 90 degrees apart, so the two bands, the two Kikuchi bands, will be 90 degrees apart as well. So that's very good. That's very good. Okay, now let's take one step further. Look at 110 planes. So 110 planes. How many 110 planes are parallel to the electron beam direction? Any guesses? I can draw one for you. So this one is parallel. Do you have another one? You do. So let me just shade this one, draw another unit cell. Another one that's parallel to the electron beam is this one. So again, you have two planes, and we know the 110 planes are 45 degrees away from the 100 planes. So here they're 45 degrees as well apart. And this is what you see if you have a crystal aligned along the 100 direction. That's the Kikuchi pattern you see. If I tilt the crystal to 110 direction or 111 direction, you can do something like that as well. But looking at the angles of these bands, you can easily deduce the symmetry of the crystal. One more information is the width of the band. This is 2 theta. For those who have done XRD, you always plot 2 theta against the intensity. Then the 2 theta information of each plane is also embedded in the Kikuchi pattern. There are a few notes before we finish today's class. So note, the first thing is we're getting those bands, but really the Kikuchi pattern, these are 2D projections of 3D objects. So Kikuchi pattern are 2D projections of 3D diffraction cones. There's a name for that, it's called Kossel cone, named after Kossel. Okay, the second thing is about the experiment setup. When you do EBSD in SEM, you always tilt the sample by 70 degrees. Which you will see very soon today in today's lab. The reason is because the detector comes in at an angle. So you want the specimen to be parallel to the detector. Again, you will see that in the lab very soon. Apart from that, let's save the rest for next week's class. Any questions about Kikuchi diffraction? I know this is non-intuitive and it's not easy to understand. Usually people study the regular diffraction first, regular electron beam diffraction first, before moving to Kikuchi diffraction. I hope going to a nightclub in energy can give you some insight to bring this concept closer to you. The main takeaway message is it undergoes scattering twice. The first time it's more like a drunkard walking, so it's random walk. But after that, it's more like a military marching. It's Bragg's diffraction. So inelastic scattering first, then elastic scattering. In the next class, we'll discuss how we are going to analyze the results, analyze the Kikuchi pattern to give us the crystal orientation.